Imagine a country almost completely swallowed by sand, a country where over 95% of the land is desert, and rainfall is so rare as to be virtually non-existent. Yet, under these conditions, Saudi Arabia has accomplished the almost unthinkable. It has built a colossal steel water supply system from the shores of the Red Sea to supply the entire country. Every day, billions of liters of seawater are drawn into massive desalination plants and then pumped across the desert through a network of pipelines stretching thousands of kilometers, carrying the water from the sea inland. The mere fact that water can be delivered so far from the coast is a remarkable engineering achievement, but Saudi Arabia has truly earned the world's respect for its ability to transform salty seawater into fresh water, fit for drinking, farming, and industry. So how is this invisible river of steel built and operated? Today, we will figure out together how she managed to do this. Saudi Arabia is home to over 37 million people, and almost the entire population is Muslim. What's particularly curious is that almost all the people are concentrated along the coast of the Red Sea and the Persian Gulf, while the interior remains a virtually uninhabited desert. This country has what the world craves: oil. But nature never gives everything at once. Despite possessing colossal oil reserves beneath its soil, the country still must spend billions of dollars to extract every drop of fresh water. Average annual rainfall here is less than 100 millimeters, and summer temperatures regularly rise above 45 degrees Celsius. To survive in these conditions, Saudi Arabia built a nationwide water supply system. To truly appreciate the scale of this challenge, it's worth considering for a moment what it means to live in such a country. There are no full-flowing rivers, no large lakes, no abundant underground springs to rely on. The sky remains cloudless for months, and scorching sand stretches to the horizon. And yet, tens of millions of people need water every day to drink, cook, wash, irrigate their fields, and supply factories. In a typical country, nature itself provides all this: rain, rivers, springs. But Saudi Arabia has to create it all from scratch, extracting water directly from the sea and forcing it to flow through the desert to where people live. Essentially, an entire nation exists thanks to a man-made system, without which life here would simply cease. This network is constructed from high-strength carbon steel pipes, almost the same as those used in the oil and gas industries. Construction costs an average of approximately $3 million per kilometer of pipeline, and that's not even counting the pumping stations that pump the water further, or the desalination plants themselves, each of which can cost tens of millions. But where does this pipeline get its water? The answer is a nearly inexhaustible source: the sea. However, seawater contains about 3.5% salt, meaning it's too salty to drink or irrigate fields with. This is precisely why desalination technology was developed, giving Saudi Arabia a virtually limitless supply of usable water. The pipeline carries water from giant desalination plants located directly on the Red Sea. Such a plant can convert millions of liters of seawater into potable water per day, consuming a huge amount of energy in the process. Energy is the key and most expensive resource here. Pushing seawater through membranes and extracting the salt requires enormously powerful pumps, running non-stop day and night. This is why desalination is considered one of the most energy-intensive methods of water extraction in the world. Saudi Arabia is fortunate in this regard. It has cheap fuel right next door, and it uses some of its vast oil and gas reserves to convert the salty sea into drinking water. It's a kind of exchange. The country generously spends one of its riches, which it has in abundance, to acquire another, which it desperately needs. But first things first. The first step in building a transcontinental water pipeline is the manufacture of the pipes themselves. They are typically made of high-strength carbon steel, similar to that used for oil and gas pipes, to withstand the constant pressure of pumping, the mechanical shocks of underground installation, and the extreme temperature fluctuations of the desert. Rectangular steel sheets are cut to pre-calculated dimensions, one that can be rolled into a round pipe approximately 1 8/10 of a meter in diameter, and with a wall thickness of almost 25 millimeters. The sheets are then passed through a multi-axis rolling mill, where rollers bend the steel step by step until the two edges meet, forming a pipe blank ready for the next step, longitudinal welding. After welding, the pipe is passed through a continuous flow water cooling system to reduce the weld temperature. Next, the steel pipes are carefully ground along all edges and corners, removing burrs and achieving precise geometry. Both ends of each pipe are machined to a beveled weld bevel, creating the best possible surface for future joints. Each pipe section is typically approximately 12 meters long, sufficient to reduce the overall number of welds while still being convenient for transportation. This length allows for quick pipe connections, maintains a tight seal under pressure, and ensures durability for years to come. It's worth explaining why such strict requirements are placed on these pipes. Underground in the desert, they face several enemies. The sand heats up during the day and cools sharply at night, causing the metal to expand and contract year after year. The water being pumped constantly presses on the inside, while the soil piles up on the outside. And the water itself, if left unchecked, will eventually corrode the steel with rust. That's why the pipes are made of particularly strong steel and coated with protective layers on the outside, so that this underground water pipeline will serve reliably for decades, remaining invisible and unnoticeable to those who use its water. Finished steel pipes are transported to an open storage area, where they are stacked in batches and clearly marked for accounting and tracking. From there, they are lifted by forklifts or cranes onto specialized transport vehicles and securely fastened to prevent deformation during transit. Finally, the pipe sections are transported hundreds of kilometers to the construction site, where they are welded together directly along the future pipeline route. The installation itself begins at large transfer areas located along the route. Here, the finished pipe sections are sorted by diameter, length, and installation sequence, and engineering crews perform a final inspection, checking the straightness of the pipes, the condition of the coating, and identification marks. Strict order at such a site is crucial. It allows for uninterrupted work and minimizes delays and errors in the harsh desert conditions. Meanwhile, surveying crews map out the pipeline's precise route through the desert, using satellite navigation, total stations, and terrain data. The route is marked directly on the ground with stakes and bright paint. This stage ensures that the pipeline will take the most stable and efficient route, avoiding soft soils, shifting sand zones, and areas prone to erosion. For a pipeline stretching for hundreds of kilometers, choosing the right route is crucial, as the longevity of the entire structure depends on it. Before digging the trench, the site must be cleared and leveled to allow heavy equipment to operate without interference. Temporary access roads are built parallel to the pipeline for trucks, excavators, welding machines, and material vehicles. Preparation also includes measures to prevent dust and quicksand to ensure good visibility and safety for workers. This is the foundation upon which all subsequent construction rests. Once the route is finally determined, large crawler excavators begin digging a trench along the marked line. It is dug to a precisely specified width and depth to ensure sufficient space for both the pipe installation and subsequent backfill. The excavated soil is immediately sorted. Suitable material is retained for backfill, while unsuitable material is removed. Maintaining a consistent depth and a straight trench line is crucial. Otherwise, the pipe may become deformed or shift after installation. In some areas, where the route crosses steep and precipitous mountain slopes, the trench is cut directly into solid rock using explosives. Charges are placed in precisely calculated locations and detonated one after another to fracture the rock along the marked line. The resulting trench is deep and wide enough to securely lay the pipe, even in places where conventional equipment would be unable to penetrate. This allows construction to be carried out through the harshest landscapes, with the pipe securely hidden underground. After excavation, the pipe is not laid directly on the bottom of the trench. First, a selected material, usually fine sand or sifted soil, is spread evenly across the entire bottom, creating a so-called bedding. This layer evenly distributes the load and reduces stress on the pipe. The bedding is leveled and lightly compacted to achieve the desired height. In the desert, with its loose and dry soil, This step is especially important for the longevity of the entire line. To lay large diameter pipelines, a construction corridor approximately 40 meters wide is prepared in advance. This allows for uninterrupted laying at an average rate of about 1.5 kilometers per day. Pipe sections are taken approximately 18 meters long to reduce the number of welds directly in the field, although this places very high demands on lifting, transportation, and precise fitting at all stages. At the welding site, a hydraulic clamp is inserted into the pipe joint, and its jaws are opened to a full 360 degrees to hold the two sections perfectly aligned both before and during the first root weld. Here, an automated welding machine is deployed, manned by approximately 80 people and dozens of specialized machines. Such a team is capable of performing up to 150 joints per day on pipes approximately 1 meter in diameter. Once the welding is complete, each joint undergoes automatic ultrasonic inspection to ensure there are no internal flaws. Then, the joint coating team cleans the surface with an abrasive blast and applies a multi-layer liquid epoxy coating, creating a durable and completely sealed protective layer. Only then are the pipes lowered into the trench and covered. The assembled pipes are lowered into the trench using pipe layers, specialized tracked vehicles designed specifically for laying large diameter pipelines. Several of these machines, each with a side boom, work in a row along the line, each lifting a different section of the pipe string using soft slings and steel cables to prevent damage to the coating. The string is evenly lifted and held suspended above the ground as the machines slowly move along the trench. Coordination between the operators is crucial here, as the slightest error can cause it to twist, bend, or touch the trench walls. Once the pipe is precisely positioned, it is lowered gradually, centimeter by centimeter, until it rests in the center of the trench on the prepared bed. All the while, surveyors constantly monitor the height, straightness, and natural curve of the pipe to ensure that no residual stress develops. This method allows for quick, steady, and highly accurate pipe laying, ideal for long, straight runs across flat desert terrain. After the pipe is laid, the trench is backfilled in several layers. The first layer is made of fine material to protect the pipe coating, and on top of that is the previously excavated soil. Each layer is mechanically compacted to achieve the required density to prevent future subsidence. In desert conditions, where the soil structure is affected by both wind and temperature extremes, proper compaction plays a key role in the pipeline's longevity. Thus, section by section, this steel artery is gradually built through sand and rock, carrying water across the country. But laying the pipe is only half the battle. The water must be forced to travel thousands of kilometers through it, and in some places even rise to elevated areas far from the shore. It wouldn't flow that far on its own. Therefore, pumping stations are placed at regular intervals along the route, the powerful hearts of the system, time after time capturing the flow and pushing it forward, maintaining the required pressure. Without them, the water would run dry after just a few dozen kilometers. It's these stations that transform the stationary steel pipe into a living, flowing artery that reaches the farthest corners of the country. But all this would be of little use without the other end of the system, the one that draws water from the sea itself. It all begins with seawater taken directly from the open ocean and directed inland, establishing a steady and uninterrupted flow of raw water for the desalination plant. First, large water intake pipes are positioned offshore, where installation crews carefully position each section before lowering it into place using powerful cranes operating from barges or offshore platforms. As the pipeline extends toward shore, the individual sections are sequentially connected into a single continuous channel, designed to withstand constant hydraulic loads. At this stage, precision in connection is crucial, as even the slightest deviation can eventually impact the line's performance and capacity. Once assembly is complete, the water intake is reinforced with support frames and securely anchored to the seabed. The desalination process itself begins with seawater being drawn through pipes leading to open intake grates. The water is collected several hundred meters from the shore, where screens and filters at the inlet trap large floating debris and prevent marine life from entering. A pipe 63 centimeters in diameter can draw up to 15 million liters per day. That's more than 10,000 liters per minute at the intake point. Powerful pumps push the seawater toward the plant. But along with the water, uninvited guests sometimes arrive. Jellyfish, crabs, and occasionally even small fish. To keep these creatures out of the system, a large grate is installed, blocking anything larger than 4.5 millimeters. Afterward, the water passes through smaller grates, which filter out the remaining large particles. The water intake is also designed to be as gentle as possible on marine life. The intake rate is deliberately kept low to prevent fish and other marine life from being sucked into the pipes along with the flow, and grates trap any large objects before they reach the water. After all, the plant draws truly enormous volumes of water from the sea, and without these measures, all coastal life would suffer. So, from the very first step, even before any treatment, engineers must consider not only the purity of the future water, but also the avoidance of harm to the sea itself. But even after the large creatures have been filtered out, the water is still full of suspended solids. The solution is a filtration process carried out in special tanks. Here, water flows downwards through layers of sand under the force of gravity. The spaces between the sand grains are so small that only water passes through, while suspended particles become trapped. Meanwhile, the sand itself continually moves downwards, countercurrent to the water flow, and the solids settle on its surface. After this stage, the water appears cleaner, but countless tiny particles remain. Everything larger than about 1/10 the thickness of a human hair is removed. Large paddles then stir the water, and 2 substances are added: sodium hypochlorite as a disinfectant and ferric chloride as a coagulant. The coagulant causes the tiny grains of sand and dirt particles to clump together into larger flakes, which then settle to the bottom of the tank. Most of the dirt has been removed by this point, but the water is still far from being as clean as required for the next step: desalination. After passing through fine filtration, the water enters the cartridge purification system, the last line of defense before reverse osmosis. Each housing contains several cartridges made of tightly pressed fiber layers, with pores ranging from 1 to 5 microns in size. Water flows from the outside into the cartridge, trapping tiny particles between the fibers, while purified water passes through the wall and continues on its way. Whenever a cartridge becomes clogged, engineers remove and replace it to ensure the system always operates at full capacity. The seawater then moves on to the most critical stage, separating the salt from the water. Salt is extremely difficult to remove because its ions cling tightly to water molecules through electrical attraction. To break this bond, the system must generate tremendous pressure. If you were inside such a desalination plant, you'd surely be amazed by its size. It's not a single unit, but rather rows of identical units stretching into the distance, hundreds and thousands of membrane modules working simultaneously. Pumps hum, water rushes through pipes under enormous pressure, and countless sensors flicker on control panels. All this machinery operates around the clock, 7 days a week, 7 days a week. Because if it stops, entire cities risk being left without water. Essentially, we're looking at a veritable water factory, tirelessly transforming the salty sea into something no human can live without. This is where the real magic begins, a process called reverse osmosis. The idea is simple. Apply pressure greater than natural osmotic pressure and force water through an ultra-thin membrane, leaving salt and other impurities behind. To create this pressure, the plant uses powerful centrifugal pumps. Each pumping system unit is responsible for its own pressure stage, and it gradually increases as the water passes through one compression stage after another. By the time the water exits the final stage of the pumping unit, the pressure reaches approximately 60 bars, roughly 60 times greater than atmospheric pressure, enough to separate water from salt at the molecular level. After the first pass through reverse osmosis, the water is almost completely free of salt, but still contains traces of ions and microscopic impurities that must be completely removed to meet certain drinking water standards. Therefore, the water is passed through a second stage of reverse osmosis, where even thinner membranes operate under lower pressure, but separate salt even more effectively. This stage reduces the water's electrical conductivity to extremely low levels, extracting the last remaining ions and rendering the water truly pure. The result is an ultra-pure stream of water of almost flawless purity, ready for mineral enrichment and distribution. But desalination has its downside, which should be honest. After all, when fresh water is removed from seawater, all the salt it once contained doesn't disappear. It remains in a thick, heavy brine, which must be returned to the sea. This brine is much saltier than regular seawater, and if discharged thoughtlessly, it can harm all living things near the shore. Therefore, efforts are made to dilute and disperse it properly, preventing it from accumulating in one place. So, turning the sea into drinking water is not only a triumph of engineering, but also a constant quest for balance with nature. True, after passing through reverse osmosis membranes, the water becomes clean enough for irrigation. However, before it's safe for human consumption, its acidity must be corrected. To do this, the plant adjusts the pH level, usually by adding a small amount of acid or a balancing solution to bring the water back within safe limits. Furthermore, desalinated water contains far fewer beneficial minerals than regular drinking water. Therefore, to improve both its taste and overall quality, small amounts of minerals, for example, calcium and magnesium, are added during remineralization. This step restores the water's mineral composition, corrects the acidity, increases the alkalinity, and restores its natural flavor, making it not only safe but also more beneficial and enjoyable for people. It's worth taking a moment to take in the entire system, from the distant water intake at sea, through rows of grates, tanks, sand filters, and membranes, through powerful pumps and dozens of purification stages, and onward, through steel pipes stretching to the horizon, through sand and rock, to cities in the heart of the desert. It's a single, seamlessly functioning mechanism thousands of kilometers long, monitored 24/7 by engineers, sensors, and control systems. Should the pressure drop or a filter become clogged, it's immediately reported. This entire colossus works non-stop to ensure that clean water flows from the tap of an ordinary citizen, hundreds of kilometers from the sea. And so, after this long journey, desalinated water finally reaches residential areas through a modern pipeline network to serve the people of Saudi Arabia. However, the price of such water is extremely high, around $5 per cubic meter, while, say, in the United States, the same volume might cost just a few tens of cents. Every sip of fresh water here requires gigantic factories, thousands of kilometers of steel pipes, powerful pumps, and colossal energy expenditures. It is at this price that life-giving moisture is born in the midst of a scorching desert where there is almost no rain. And yet, for a country almost entirely engulfed by sand, this high cost is not a wastefulness, but a matter of survival. There is simply no other way to provide water for an entire nation. This is the invisible river of steel, one of the most astonishing engineering feats of our time, transforming a salty sea into a source of life for an entire people. If you are interested in taking a peek inside this amazing process, stay tuned. There are many more stories ahead about how humans are conquering nature.